The concept of enthalpy relates to the flow of energy during a chemical process. One way to determine enthalpy is by taking mass times the specific heat constant times the change in temperature. Another way to calculate the enthalpy of a reaction is to take the potential energy of the products and subtract the potential energy of the reactants. A third way to determine the enthalpy of a reaction is to use Hess's law. Two or more reactions can be added together to determine the delta H of a reaction. Hess's law problems involve using your enthalpy table to solve a puzzle. You are given a reaction not on the enthalpy table. You have to manipulate two or more of the reactions on the table in order to add them together and produce the reaction of interest. You will always be told which reactions to use, but sometimes you'll be told how to manipulate those reactions, and sometimes you have to figure out how to manipulate the reactions. Let's work through several examples. For the first example, we want carbon dioxide producing carbon monoxide and oxygen gas. To get this reaction, we have to add together the reverse of reaction 11 and reaction 14 as written on the table. Reversing reaction 11 results in this reaction, and writing down reaction 14 is as simple as this. Now we need to add these reactions together. We are going to start by canceling any substance that appears on one side of the arrow in one equation and the other side of the arrow in the opposite equation. Like carbon, notice one carbon is produced in the first reaction and one carbon is a reactant in the second reaction. These carbons will cancel. Oxygen will also cancel in the second reaction. One oxygen is produced in the first reaction, while a half oxygen is a reactant in the second reaction. The 1/2 oxygen will cancel, and the O2 in the first reaction will become 1/2 O2. The same concept applies for the enthalpy values. Notice that the first reaction is endothermic, while the second reaction is exothermic. So to get the appropriate enthalpy value for the overall reaction, you have to subtract those terms. Since 94.05 is larger than 26.4, we know the overall reaction will end up being endothermic. We simply have to subtract these two enthalpy terms to get the new enthalpy value for the overall reaction. In this case, 67.7 kcals. Notice that we now have the overall reaction that we are trying to achieve. 1 CO2 plus 67.7 kcals produces 1 carbon monoxide and 1/2 O2. Now let's answer these questions. Is the reaction endothermic or exothermic? Remember, for an endothermic process, the energy will be on the reactant side, while for an exothermic process, the energy will be on the product side. Since we have 67.7 kcals of energy as a reactant, this is an endothermic process. Is more energy stored in the products or reactants? There are two ways to look at this. The first thing you can do is consider an energy diagram for an endothermic process. Here you can see for an endothermic process, the products have a higher energy than the reactants. The other way to think about this involves the law of conservation of energy. Remember that energy must be conserved during a chemical reaction. Well, in order for energy to be conserved for this reaction, 67.7 kcals of energy has to be added to the reactant side. That means the products have to be higher in energy because energy had to be added to the reactants just to make the energy of the reactants equal to the energy of the products. So the products have more energy. This will always be the case for an endothermic process. What is the heat of reaction for 1 mole of CO2? This question is pretty simple for this reaction, since in the overall reaction we only have 1 mole of CO2. That means the molar relationship between CO2 and energy is 1 mole of CO2 requires 67.7 kcals of energy. Now the energy must be absorbed because the process is endothermic. When we report this answer, we must include the sign. we have to write positive 67.7 kcals as the relationship to 1 mole of carbon dioxide. In this next example, the reactions that you need to use are given, but you are not told how to manipulate them. You must figure that out on your own. To do this, try to find a substance that is unique to the equation you're supposed to use and to the overall reaction. For example, Al2O3 must be a product in the overall reaction. Well, when you look at reaction 9 and reaction 11, Al2O3 is only in reaction 9. Reaction 9 must be manipulated so that aluminum oxide is a product and we have 2 aluminum oxides produced. Aluminum oxide is already a product in reaction 9. However, we will have to multiply reaction 9 by 2 so that 2 aluminum oxides are produced. When we compare reaction 11 to the overall reaction, we need carbon dioxide to be a reactant and carbon to be a product. Therefore, we have to reverse reaction 11. Also notice that we need 3 carbon dioxides and 3 carbons in the overall reaction. So, we also know we need to multiply reaction 11 by 3. We are ready to add these reactions together. 3 O2s will cancel. By observation, we can tell that this reaction is going to be exothermic. So we're going to take 800 kcals minus 282.15 kcals. This will give us 517.85 kcals. However, we must follow our sig fig rules for addition and subtraction. 800 has no decimal places. Therefore, our new kcals cannot have any decimal place value. So round to 518 kcals. When we add the reactions together, we get 4 aluminum plus 3 carbon dioxide produces 2 aluminum oxides plus 3 carbons and 518 kcals of energy. Since the energy is a product, this reaction is exothermic. Is more energy stored in the products or the reactants? Once again, let's look at this 2 different ways. Consider the energy diagram for an exothermic process. You can see for an exothermic process, the reactants have a higher energy than the products. You can also think about this in terms of the law of conservation of energy. Look, energy must be added to the product side just so that the products have the same amount of energy as the reactants. So the reactants have more energy. This will always be the case for an exothermic process. What is the heat of reaction per 1 mole of aluminum? Well, 518 kcals of energy is released for 4 moles of aluminum. To get the amount of energy released for 1 mole of aluminum, you must take 518 kcals divided by 4. This gives you 129.5. But you can only have 3 sig figs, so the answer rounds to 130 kcals. Don't forget that decimal point, or the number is only 2 sig figs. Also, do not forget the sign. Since the process is exothermic, the value must be reported as a negative 130 kcals. Okay, your turn to try some. In this example, you are told how to manipulate the given equations. 2 times the reverse of reaction 21 should give this. 2 times reaction 25 should look like this. And reaction 3 is simply this. Pause the video and try to add these reactions together on your own. When you think you have it, press play and check your work. Since 96.7 kcals of energy appears on the reactant side, this reaction is endothermic. For all endothermic processes, more energy is stored in the products. 96.7 kcals of energy is required for 2 moles of HF, so for 1 mole of HF, simply divide 96.7 kcals by 2. Rounding to the appropriate sig figs results in 48.4 kcals of energy. Since the reaction is endothermic, this value must be reported as a positive 48.4 kcals. For this reaction, you must determine how to manipulate the given equations. Pause the video and try to figure this one out on your own. When you think you have it, press play and check your work. This reaction is exothermic because energy is a product. The reactants store more energy for all exothermic processes. And this is another easy one. Since the overall reaction is in terms of 1 mole of propane, 488.6 kcals of energy are released per mole of C3H8. Since the process is exothermic, the value must be reported as negative.